Right now, while you are sitting here reading this sentence, our own sun is doing something it has been doing quietly for over 4.5 billion years, something almost nobody thinks about on a normal Tuesday. It is getting brighter and hotter every single day, by an amount so small you'll never notice it in your lifetime, but so relentless that scientists can already trace its fingerprints in Earth's rock record right now. It runs on a nuclear furnace roughly the size of 1 million Earths stacked together. And the process that will eventually end life on this planet isn't some distant future event waiting to begin. It's already underway. Scientists aren't calling this concerning. They're calling it inevitable, mathematically certain, and in some ways, already measurable in the deep past of our own climate. Here is the part the headlines are not telling you. Stay with me, because by the time this is over, you will never look at a sunny afternoon quite the same way again. Our story doesn't begin with an explosion. It begins with the slowest, most patient chemical reaction imaginable, one that has been running, uninterrupted, since before life existed on Earth at all. Deep inside the sun, roughly 400 million tons of hydrogen are fused into helium every single second, a reaction so efficient it converts a small fraction of that mass directly into pure energy, following the same equation a schoolchild learns in physics class, E equals mc squared, playing out on an industrial scale in the sun's core, non-stop, for 4.5 billion years. This is not new information. Astronomers have understood the basic mechanics of stellar fusion for roughly a century now. What's newer and stranger is exactly how precisely we can now model what happens next using data that simply didn't exist a generation ago. To picture the scale of that furnace, the sun converts roughly 4 million tons of pure mass into energy every second, and yet, because it is so enormous, that staggering loss barely registers against its total bulk, which is so large that it contains more than 99% of all the mass in our entire solar system combined. Even at that rate of consumption, the sun has enough hydrogen fuel remaining in its core to keep burning, largely as it does today, for roughly another 5 billion years, a number so large that comparing it to a human lifetime is almost meaningless, the equivalent of comparing the width of a human hair to the distance across an entire ocean. Here is where the first twist in the story arrives. As the sun burns through its hydrogen fuel, its core doesn't stay the same. It slowly, steadily shrinks and compresses under its own gravity, which, counterintuitively, makes the fusion reaction inside burn hotter and faster, not slower. This means the sun has never actually been a stable, unchanging light bulb quietly burning at the same brightness since it formed. It has been getting brighter, gradually, continuously, for its entire existence, and current models suggest it is now roughly 30% more luminous than it was when Earth was young, 4 billion years ago. 30%. Not from some dramatic explosion. From the slow, patient math of gravity and fusion, quietly accumulating for billions of years. But here is the part that stops being abstract and starts being personal. Geologists have found direct evidence in ancient rock formations, in the chemical signatures locked into billion-year-old sediment, that Earth's climate has already had to compensate for a fainter, cooler young sun in the deep past, something researchers call the faint young sun paradox, because a 30% dimmer sun should have frozen the early ocean solid, and yet the geological record shows liquid water instead. It runs, essentially, on a delicate balancing act between a slowly brightening star and an atmosphere that has had to continuously adjust for billions of years just to keep the surface of this planet within a survivable range. Scientists still don't fully agree on exactly how early Earth pulled off this trick. Some point to a much thicker blanket of greenhouse gases in the ancient atmosphere, others to subtle differences in cloud cover, and others to a combination of both working together in ways we're still refining with newer climate models. What everyone does agree on is the underlying mechanism. Earth's atmosphere has never been a fixed, static thing. It has been quietly renegotiating its relationship with an ever-changing sun for the planet's entire 4.5 billion year history, adjusting, compensating, and buying time, the same way a thermostat keeps nudging the temperature back toward comfortable, except this thermostat has been running continuously since before life itself existed. Think about what that actually means. Every single day you've ever lived, every sunrise you've ever watched, has occurred under a star that is, right now, in this exact moment, incrementally brighter than it was for every previous generation of humans, every dinosaur, every early microbe that ever existed on this planet. Now the story gets stranger. This slow brightening isn't a footnote. It's the entire reason Earth eventually stops being habitable, long before the sun ever runs out of fuel entirely. Current climate models suggest that in roughly 1 billion years, give or take a few hundred million, the sun will have brightened enough that it fundamentally breaks Earth's carbon cycle, the very same slow thermostat that has kept our climate stable for billions of years by pulling carbon dioxide out of the atmosphere as temperatures rise. Once temperatures climb high enough, that thermostat effectively runs out of room to compensate. Atmospheric carbon dioxide crashes toward levels too low for most plant life to survive, and Earth's oceans begin evaporating faster than they can be replenished. The mechanism is almost quietly ironic, given how much attention carbon dioxide gets today for entirely different reasons. Right now, rising carbon dioxide traps heat. But over the coming billion years, as the sun's own brightening takes over as the dominant driver of temperature, the planet's natural weathering processes, rock breaking down and absorbing carbon dioxide faster in a hotter world, will start pulling that same gas out of the atmosphere so aggressively that plant life, especially the more common types of photosynthesis most of Earth's vegetation relies on today, will begin struggling to survive. Not because of too much heat directly, but because the very gas plants need to breathe becomes scarce, even as the world around them keeps getting hotter. Here's the twist that almost nobody outside planetary science circles is talking about. This isn't a slow fade into a slightly warmer version of today. Once the runaway phase begins, models suggest it could unfold over a period as short as a few 100 million years, eventually leading to Earth's oceans boiling away entirely, leaving behind a scorched, Venus-like world with a thick, crushing atmosphere and surface temperatures hot enough to melt lead. 1 billion years sounds unimaginably distant, and it is roughly 200 times longer than complex animal life has existed on Earth. But compared to the sun's total 10 billion year lifespan, it means Earth will spend less than 15% of the sun's remaining life actually habitable for anything resembling the biosphere we have today. Stop and sit with that for a second. We tend to imagine Earth's habitability as basically permanent, something that will simply continue as long as we don't ruin it ourselves. But the honest, uncomfortable math is that Earth has a built-in, ticking expiration date written directly into stellar physics, one that has nothing to do with anything humanity does or doesn't do, and everything to do with a nuclear furnace 93 million miles away slowly turning up its own dial. If the sun's brightening alone doesn't end things first, its eventual transformation certainly will. In roughly 5 billion years, once the sun exhausts the hydrogen fuel in its core entirely, it will begin fusing hydrogen in a shell around a contracting helium core, causing the outer layers to swell dramatically, transforming our familiar yellow sun into a bloated red giant star, potentially large enough to expand out past Mercury, past Venus, and by many current calculations, uncomfortably close to Earth's current orbit, if not swallowing it outright. Mercury and Venus have almost no realistic chance of surviving this phase intact. Most models agree they will be engulfed entirely, their surfaces vaporized into the sun's expanding outer atmosphere. Earth sits in a genuinely uncertain middle zone, close enough that older models simply assumed it would be consumed along with its inner neighbors, but recent, more detailed simulations factoring in exactly how much mass the sun loses as gas and radiation during this phase have opened up a real possibility that Earth's orbit could widen just enough, at just the right pace, to survive as a physical object, even if every trace of its atmosphere and oceans has long since been boiled away by then. A signal traveling at the speed of light currently takes about 8 minutes to reach us from the sun. During the red giant phase, that same sun could physically expand across a volume large enough that its outer surface reaches roughly where Earth is orbiting today, though newer research complicates the picture, because as the sun swells, it also sheds mass, weakening its gravitational grip, which could allow Earth's orbit to drift slightly farther outward over that same span of time, a gravitational tug-of-war between an expanding star and a slowly retreating planet that scientists are still actively modeling and debating today. Come back to the science, because there is one more thing worth knowing. In recent years, researchers studying other sun-like stars nearing the end of their hydrogen-burning phase have actually observed, in real time, distant solar systems believed to be consuming their own inner planets during this exact red giant transition, essentially giving astronomers a preview, from thousands of light years away, of a fate that may be waiting for our own solar system. These observations, made possible by newer, more sensitive space telescopes, have allowed scientists to refine their models of exactly how a star's expansion interacts with the orbits of nearby planets, sharpening predictions about Earth's own long-term fate with a level of confidence that simply didn't exist a decade ago. And now comes the moment on the calendar, already locked in, whether we like it or not. Somewhere around 7 to 8 billion years from now, having shed its outer layers into a glowing shell of gas, the sun will finally settle into its true final form. A white dwarf, an Earth-sized, impossibly dense stellar ember slowly cooling for trillions of years, radiating away its last heat into the darkness long after anything resembling a solar system, in the way we understand it today, has ceased to exist in any recognizable form. A white dwarf like the one our sun will eventually become doesn't go out with any kind of dramatic final act. There's no explosion. That fate is reserved for stars far more massive than ours. Instead, it simply sits there, an Earth-sized ball packed with roughly the same mass the entire sun has today, so dense that a single teaspoon of its material would weigh several tons here on Earth, slowly, quietly radiating its remaining heat into space over a timescale so long, trillions of years, that the current age of the entire universe would only represent a small fraction of that final cooling process. There is something almost unbearably poetic in that. The same star that has warmed every sunrise in human history, the same star ancient civilizations worshipped, tracked, and built entire calendars around, will eventually shrink down to roughly the size of the planet it once helped bring life to, a slow-burning ember drifting through a solar system with no planets left to warm. And yet, on the scale of the sun's own 10 billion-year story, humanity's entire existence occupies a sliver of time so brief it barely registers as a rounding error, a species that showed up in the last 100,000th of the sun's total lifespan, just long enough to notice, measure, and start worrying about an ending unfathomably far in the future. There are still two genuine open questions science has never fully resolved about this timeline, and neither has an easy answer. The first, will Earth actually be consumed by the expanding sun, or will the gradual loss of the sun's mass push Earth's orbit outward just enough to survive as a charred, lifeless husk drifting at a slightly safer distance? Current simulations genuinely disagree, with results sensitive to tiny assumptions about exactly how much mass the sun sheds and when. The second question is stranger still. Could any future form of life, human or otherwise, actually relocate an entire biosphere to a different world before any of this becomes an emergency? And if so, on what kind of timescale would that even need to begin, given that the danger doesn't arrive suddenly, but creeps in slowly, over hundreds of millions of years, easy to ignore until it very much isn't? That window, the almost unimaginably long stretch of time in which Earth remains comfortably habitable exactly as it is today, is closing, slowly, year by year, in a process too gradual for any human lifetime to notice, but too certain for physics to ever reverse. So the next time you feel the sun on your skin on an ordinary afternoon, remember this: that warmth is coming from a star that has been quietly, patiently getting brighter for 4.5 billion years, and will keep doing so, long after every person alive today, and every person who will ever be born, is gone. It was never going to stay exactly the same forever. It just never stopped changing. And the changes that end life on Earth, according to the numbers, have already begun. If this story pulled you into the deep, dark math of it, subscribe right now. Drop a comment telling me whether you think humanity will still be around to see any of this unfold. And share this with someone who's never thought about the sun as anything other than permanent, because Earth's slow motion ending is already written into the physics, and almost nobody is talking about it.